Alright guys, welcome to lesson 3.2. We're going to continue our talk about limits. Now last time we learned what a limit is. It's the y value that a function approaches as x approaches something. And we looked at that and analyzed it by looking at tables last time. Well, we're going to do the same thing today, but we're going to do it by looking at graphs instead of tables. So the first thing we're going to do is we're going to find the limit of a function by looking at a graph. You'll appreciate this. It's a lot less work and not quite as tedious as the other one. We'll also learn how to distinguish limits at infinity from infinite limits. Those are two different kinds. They sound the same, but they are different. There's the limits at infinity, and then there's infinite limits. And we'll learn what the difference between those two types of things are. And then we'll identify three cases where the limit can fail to exist. We saw two last time, but we're going to look at three more specific ones today. And those are all going to be from the perspectives of graphs. So here we go. Now when you're looking at a graph, your x values are on the horizontal axis and your y values are on the vertical axis. Alright, so let's take a look at number one. Now the first thing you want to look at when you're doing a limit by graphs is you want to look at this part down here, because it's telling you what we're doing. Now what this means is we are approaching we're approaching an x value of -2, but since there's a little plus right here, that means we're approaching -2 from the right of -2. So first of all, let's find where x equals -2 on this graph. That would be right here, correct? Now if I'm approaching that graph from the right, that means I'm approaching it this way. So I'm coming at it from this direction. Now as I get closer and closer to that dot, the question is, what y value is it getting closer and closer to? Well, the y value it's getting closer and closer to in this case is -2. Just coincidence that the x value and the y value are the same, but I'll write the coordinates of the point. So basically, as I approach an x value of -2 from the right side of the graph, I'm getting closer and closer to a y value of -2. So this one, the limit of f of x as x approaches -2 from the right is -2. All right? Let's go ahead and take a look at number 2. What is the limit of f of x as I approach -2, the same number from the left? Well, I'm still trying to reach this spot here where x equals -2, but this time I'm coming at it from the left. So I'm starting here, and I'm getting closer and closer and closer and closer to that x value. As I get closer and closer to that x value of -2, what y value am I approaching? It's still -2. It's the same spot. So you're like, okay, Mr. Bailey, this is kind of stupid. Well, it'll make more sense as we get through more problems. But what this indicates, you guys, is that since as I'm approaching -2 from the left and from the right, I get the same answer both times. You know what that means? That means the limit exists for that particular point. And so compare number 3 to numbers 1 and 2. It looks exactly the same. It's just that I don't have a little plus or a minus after the 2. And that means that we're just talking about the limit. These ones up here are what we call one-sided limits. We're approaching from the right or approaching from the left. But here, we're just talking about the limit, which is approaching from both sides at once. And as we learned last time, when the limit from the left and the right are the same, then the limit exists. And so the limit of this function as x approaches -2 is -2. Awesome, right? Now, this is going to seem stupid also, but just bear with me. It won't seem stupid after we finish. What is f of -2? Now, when I write this, I'm not asking what is it approaching. I'm asking what is it. So when x equals -2, what is the y value? Well, the y value is -2. Oh my gosh, they're all -2. So this is stupid, right? Well, not yet, right? Just buckle up. Just wait for me. We'll get there. But here's what I want you guys to interpret this as. If I approach from the right, it's 2. If I approach from the right, the y value approaches -2. If I approach from the left, the y value approaches -2. Therefore, the limit exists. And also, as an added bonus, not only do we approach 2, but the actual y value is 2. Now, the reason why I'm spending so much time on this is because it's possible that this won't happen again in other circumstances, and I'm going to show you as we get to the other ones. But this is a unique circumstance where the right and left are the same, so the limit exists, and it just so happens that that's what the function actually equals at that point as well. So let's go ahead and take a look at some other situations now. Let's take a look at number 5. So what x value am I approaching first of all? I'm approaching 3. From which side? The right side. So let's find our spot where x equals negative 3. There's 2 places where x equals negative 3. Here and here. Now, just so you understand though, this is an open dot and this is a closed dot. So I'm going to circle this dot, but just know that I can approach that dot, but I can't actually get there because that's an open dot, which means that spot does not exist. Here is where x actually equals 3. So I'm approaching 3 from the right. Now, if I'm approaching 3 from the right, then I'm coming at it from this direction. Now, as I approach 3 from the right, what y value am I approaching? In other words, what y value are these arrows getting closer and closer to? Well, the y value that these arrows are getting closer and closer to is negative 2. So as I approach 3 from the right, the y value that I'm approaching is negative 2. So I'm going to put negative 2 here. Now, once again, I want you to understand, that's not what the y value actually is. The y value is actually down here. The y value is actually negative 3. But the y value we are getting close to as we approach from the right is negative 2. Let's take a look at the next one. I'm still approaching 3, but this time I'm approaching it from the left. So that's going to look like this. Now, what y value are we approaching? Well, not surprising, it's the same thing again, so it's negative 2. Okay, fine. So you know what that means? Since the limit from the right and left are the same, well, that's what the limit is. So far you're like, okay, Bailey, it's just as stupid as the last one. Well, no, not yet. We're about ready to actually see something interesting happen right now. So here it is. The next question asks us, well, what is the y value when x equals negative 3? Well, when x equals negative 3, we're not at this open dot anymore. We're actually down here. This is where the dot actually exists. That's where the function is defined. And so f of 3 is not negative 2 this time. F of 3 is negative 3. So we have a little bit of a difference there. Okay? Let's look at something else that makes things even a little bit more different. So for this point here, left and right were the same, and that's actually where the point exists. Here, left and right were the same, but that's not where the point exists. The point exists down here. So even though the limit existed up here, the function was different. It was down here. All right, let's take a look at one more scenario for numbers 9 through, well, actually maybe 2 more scenarios. So we'll look at one more for 9 through 12 here. So in this case, what number am I approaching on number 9? I'm approaching negative 4. From which side? The left, because there's a little minus sign there. So if I approach negative 4 from the left, let's see what that looks like. Well, here's where x equals negative 4. Now there's 2 spots once again. I've got a closed dot and an open dot, right? And we know that the closed dot is the point that actually exists. But that doesn't matter when we're doing limits. When we're doing limits, we're approaching from directions, right? So I'm approaching from the left. So I'm going to approach negative 4 from the left. Now, as I approach from the left, these arrows are getting closer and closer to what y value? They're getting closer and closer to a y value of 2. How about if I approach negative 4 from the right? Well, if we're coming at negative 4 from the right, well, now we're coming in on this side. And if I come in on this side, getting closer and closer to an x value of negative 4, now what y value am I approaching? We're approaching a different y value. Now I'm approaching 3. Uh-oh, the left-handed limit and the right-handed limit don't match. You know what that means about the limit in general? That means the limit does not exist. Because the limit from the left and right were not the same. Now here's the next question. what is f of negative 4? In other words, we're not asking what is y approaching. We're asking what does y actually equal when x equals negative 4? Well, the closed dot is the one that we use for that. That's where the actual y value is. So the y value is actually 2. All right, one more question. Now in this question, I'm not going to do it the same way I did the other ones, and yet I am. So what do I mean by that? Well, look at it. I'm saying what is the value, what is the limit of f of x as x approaches 0? Now first of all, let's find where x equals 0. That's like right here on my graph. Okay? Now, but you'll notice I didn't put a plus or a minus, so what do? Well, if there's no plus or minus, you guys, that means they want you to come from both directions. They want you to come from the left, and they want you to come from the right. And if they meet at the same spot, which they do, they want you to say what's the y value. So since the limit from the left and the limit from the right are both meeting up at the same spot, what is the y value of that spot? Well, that spot looks to me like I would estimate that to be about negative 1.5. And I can only estimate because they didn't actually give me a coordinate there. But there you go. So the reason I included number 13 was so that you guys know that if they don't put a plus or a minus here, that means they want you to come from both directions. And if it actually exists, then that's the answer. All right. Let's let you guys try some. So here's a student practice slide. Go ahead and pause the video, and when you unpause the video, I'll have all the answers up for this one. All right, so there's our solutions there. If I'm approaching negative 4 from the right, I'm just going to use my little arrow, my cursor here. You guys can follow it. If I approach negative 4 from the right side, I'm approaching a y value of 0. For number 2, if I'm approaching negative 4 from the left, I approach a y value of negative 1. Since those are different limits from the left and right for that same x value, then we would say that the limit on number 3 does not exist. The y value, which is what number 4 is asking for, though, however, is where the solid dot is, and that y value is 0. Now for number 5, they're talking about approaching 2. Now as you guys can see here, from the left and from the right, they're the same, and that's also where the solid dot is. And when that happens, all the answers are going to be the same. They're all negative 1. The last thing we'll look, well, no, I keep doing that. It's not the last thing. The next thing we'll look at is approaching positive 4. Now if you're approaching positive 4 from the right or left, either way you end up at this open dot, which has a y value of negative 1. So the left-handed, right-handed limits are both negative 1, so the limit is negative 1. But the y value for number 12 is actually different because it's a closed dot down here, and that's at negative 2. Finally, on number 13, we're approaching 3. Now, since it just says we're approaching 3, that means they want you to approach 3 from the left and the right. And whether you're coming from the left or the right, you're landing at the same spot here, and that y value is about positive 0.5. Okay? And so there's our solutions for student practice number 1. All right, let's continue our journey here. Let's talk about infinite limits versus limits at infinity. Okay? Infinite limits are like the ones that we saw last time in our class, where as x approaches a number, the y values just keep getting bigger and bigger and bigger, or they just keep getting smaller and smaller and smaller. So in other words, the y values approach infinity. Okay, and we saw last time that they look like vertical asymptotes. So once again, if you want to draw a picture, you can. So if I call this the x value c that I'm approaching, as I approach it, the y value shoots up way high or way low. Those are what we call infinite limits. Remember, the limit is a y value, and this is the adjective describing it. So the y value is infinity. It never stops getting bigger and bigger and bigger. Now this is different though. Over here, we have limits at infinity. Okay? In this case, it's not the y value that's infinity, but rather the x. What the heck does that mean? I'll draw you guys a picture. Last year, you guys probably learned about these things called vertical asymptotes. So let me just say, not vertical, horizontal asymptotes. Horizontal means it's a flat line. I'm going to make a dotted flat line here. Now, as you guys know, a lot of graphs just keep going on forever and ever. So I'm never going to stop moving to the right. And so my x value in that case would be positive infinity because I'm going to the right forever. It never stops. There is no limit to what the x value is. I'm just going to keep going to the right forever. That's what this means here. We're going to the right forever. But as you guys can see, as I keep going to the right, my graph is getting closer and closer to that dotted line. And that is a specific y value. The y value is not getting bigger and bigger and bigger. It's actually approaching a y value as the x gets bigger and bigger. So that usually indicates that we have a horizontal asymptote that we're looking at. So if the y value actually approaches some number as x approaches infinity or negative infinity, then we would say that's a limit at infinity. Okay? So let's review real quick. Infinite limits are whenever your x is approaching a specific number, but the y values just get crazy big and they never stop increasing. That is an infinite limit. The opposite of that is where your x value is approaching bigger and bigger numbers. It never stops moving to the right or to the left. But as you do, the y is actually reaching a specific number. These ones are very often, the infinite limits are often associated with vertical asymptotes. Limits at infinity are oftentimes associated with horizontal asymptotes. Now, here's one final situation. You can have both at the same time. In other words, you can have an infinite limit, which means the y value goes to infinity. You can have an infinite limit at infinity. That means as x goes to infinity. In other words, as x gets bigger and bigger and bigger, y gets bigger and bigger and bigger. And actually, that's a lot of functions are like that. I mean, just take, for example, a parabola. As I move to the right with a parabola, the x value keeps getting bigger and bigger and bigger, but so does the y value. It keeps going up. So as I go to the right forever, the graph goes up forever. And that's an example of an infinite limit at infinity. And so we have these two situations here, infinite limits and limits at infinity. And then you can actually put them together as well to get infinity all over the place. So let's go ahead and kind of look at what are some problems that we can ask you then about these sorts of things. So I've got part A here and I've got part B. Part A are examples of infinite limits. Why? Because infinite limits are y values that are going to infinity. Okay, that's what infinite limits mean, is that the y values are going to infinity. So let's see what they are. For number 1, what x value am I approaching? I'm approaching 3. From which side? The right side. So coming over here to my graph, here's where x equals 3, and I'm approaching that from the right side. Now as I approach that from the right side, notice this graph just starts turning up and the y values get higher and higher and higher. They never stop. In which way are those y values going? They're going up. So therefore that would be positive infinity. What about if I'm approaching 3 from the left? Well, that's going to be on the other side. Now if I approach x equals 3 from the left, now my y values are going down really fast. That would mean the y values are approaching negative infinity. Now I want you guys to be aware this is just one example. If the line had looked like this, then the left side would have been infinity also, instead of negative infinity. Okay, so don't think these are always going to match. Don't think that just because the x value is approaching positive, that the y value is going to be positive. That's not true. It depends on which way the y is going. If we're going up, that's positive. If we're going down, that's negative. Okay. So what's our answer? Well, we learned before that if they were both positive infinity, I could say infinity. Or if they were both negative infinity, I could say the limit is negative infinity. But they're not the same, so in this case we say does not exist. Okay? All right, let's take a look at part B. Now we're changing gears a little bit. We're not looking at the y values so much anymore as we're looking, well, we are, but the point I want to emphasize to you guys is that when we're talking about limits at infinity, we're talking about the x value going into infinity. Okay? Now with y going to infinity, that could mean up for positive infinity or down for negative infinity. But when you're talking about x, positive infinity means right and negative infinity means left. Okay? So when you look at this here, the limit as x approaches negative infinity, maybe make a little arrow here and make a note to yourself. This means we're going to the left. And I'm going to put forever here. All right. So this means we're going to the left forever. So I'm going to start here. You could really start anywhere, but I'll start here. And I'm just going to start going to the left. Just follow my dots. Now as I go to the left, that means I'm just going to keep doing that. As I go to the left forever, it's never going to stop moving to the left. But as you can see, that there's like this little dotted line, which is like an invisible boundary line that the graph can't cross. But it is getting closer and closer to that dotted line. So what's the limit? Well, the limit is the y value that it's getting closer and closer to. So what is the y value of this invisible barrier that the line's getting closer and closer to? Well, as you guys can see, it's getting closer and closer to a y value of 1. What about this? What does this mean? This means I'm moving to the right forever. So I'm going to be going this way. I'm just going to put some little dots here, and as I go over this way forever, never stops going to the right. But as you can see, once again, that invisible horizontal boundary is where it's getting closer and closer to that invisible horizontal boundary there, and the y value of that boundary is 1. So as x goes off into infinity, the y value gets closer and closer to 1. And you'll notice that it's the same on both sides. Okay, but we can't put these together in this case and say that the limit exists because we're actually going in different directions. So we'll just leave it at that. But there you go. So limits, infinite limits, are when you're approaching some specific x value, but your y value goes up or down. Up is positive infinity, down is negative infinity. Infinite limits have an answer of infinity. Limits at infinity actually have an answer that's a number. The infinity for limits at infinity is actually down here in the x. And what they mean is that your graph, go to the left forever or go to the right forever and see what y value you're getting closer and closer to. All right. So let's go ahead and toss one of these your guys' way. So go ahead and pause the video here, and when you unpause it, we will have the answers available for you. All right, so here's our solutions. What is the limit of our function as x approaches negative 2? The answer is it does not exist. Why? Why is that? Well, because notice they didn't put plus or minus. And when they don't do that, that means you need to come from both sides. Now, if you're approaching negative 2 from the right, you get positive infinity. But if you approach negative 2 from the left, you get negative infinity. So since the infinities are different, we're going to put does not exist. For number 2, this is asking us, what is the limit of our function as x goes to negative infinity? Now, that means that we're going to be moving to the left forever. And we're going to ask ourselves, as I keep going to the left forever, what y value are we getting closer and closer to? Well, the horizontal line that it's approaching is right here, the x-axis. It's getting closer and closer to the x-axis. So what's the y value that it's getting closer and closer to? Well, the answer is 0. Same thing happens for number 5. I'm going to skip down to there. For this one, x is approaching positive infinity. That means we're moving to the right forever. And we're approaching the same y value. That horizontal asymptote is the same on both sides. So the y value for that one is also 0. Back to number 4. What is the limit as I approach 3 from the left? Here's this vertical dotted line here represents 3. And we're approaching from the left. That's going to be coming from this way. So that's negative infinity. For number 6, we're approaching negative 2 from the right, which we did earlier anyway, but it's right here. And that's positive infinity. Now number 7 is asking us which of the limits above are one-sided limits. Those are the ones where you have a number with either a plus or a minus in the corner. So that would be the ones that we did for numbers 4 and 6. Which of the limits above are infinite limits? Infinite limits are the ones that have infinity for an answer. So that would be numbers 4 and 6. Now, number 1 is also an infinite limit. I just couldn't give an infinity as an answer because the infinity was different on the left and right. But both of those are infinities, right? So that's still technically an infinite limit for number 1. Number 9, which of the limits above are limits at infinity? That would be numbers 3 and 5 because, well, I guess I've messed up the numbers. Let me back up a little bit. I didn't realize I misnumbered my paper here. Let's see if these are still right. Just a second. I'm going to make some corrections. Okay, so if I leave the numbering the way it is, the ones that are limits at infinity is 2 and 5. And that's because x is approaching an infinity for those problems. And those are what we call limits at infinity. Okay? So there is that. Final thing I want to share with you guys is just situations where limits don't exist. Okay? Now, last time we talked about the first two already. But we talked about them last lesson when we were looking at tables. Anytime you have an infinite limit, in other words, a vertical asymptote, like these, that's one way that a limit may fail to exist. Another way that a limit may fail to exist is, as we learned last time in the tables, if the limit from the left and the limit from the right are different. We call those jump discontinuities. And the reason we call those jump discontinuities is because as you're moving along, it suddenly jumps down to another piece. Okay? So we call them jump discontinuities. Discontinuity because the line's not continuous, it's broken, which we'll talk about more in other lessons. But anyway, if the limit from the left and right are not the same, then it's a jump discontinuity. Now here's another one. This is a really weird one. It doesn't happen very often. But there are some situations where as you get closer and closer to a graph, it just jumps up. It's like this happens with trig functions primarily. So with trig functions, as you guys know, they wiggle up and down, right? Well, if you set up a trig function appropriately, as it gets closer and closer to a certain value, it's not only going to keep jumping up and down, but it's going to do it faster and faster. And in fact, as you get closer and closer to 0 here, it just starts wobbling up and down so fast that it never is really reaching anything. As you get closer and closer to 0, sometimes it's way up here. And then you get closer to 0, now it's way down here. Then you get closer to 0, up here, down here, up here, down here. It never makes up its mind because it's just wiggling back and forth constantly. And we call that an oscillation. In that case, since it's never making up its mind where it's trying to get to, we would say the limit doesn't exist once again. So those are 3 situations in which the limit may fail to exist, and how you can identify them by looking at a graph. If you have a vertical asymptote, that's a great indication that you have a non-existent limit because it's an infinite limit. If you have a break in the line like this, that's called a jump discontinuity, and the limit doesn't exist because the right and left hand limits are not the same. If you see this weird looking situation, that's what we call an oscillation, and that's another thing where the limit does not exist. And that does it for lesson 3.2.